In this video, we're going to be discussing how we can assess the model fit for confirmatory factor analysis models, and many of these concepts will extend to our structural equation models. We'll also discuss how we can modify the models and some statistics that we can use to help and guide theoretical modifications to models that hopefully make sense. So, first, let's discuss the different options that we have to assess fit. There's a large variety of these, and not really a clear consensus on which is best, though research is ongoing, and there's constantly more simulation studies that are showing this one works well in this situation, this one works well in others. One of these simulation studies, one of the classic ones that is often referenced is by Hugh and Bentler and offers some guidance in terms of what to select, different cutoffs to use for these different fit statistics, etc. One of the other things we'll talk about in this section is how when we compare multiple model possibilities, which is common in CFA and SEM, that we have several models, we're seeing which one works best, that there's a separate set of statistics that we can use. I mentioned we'll talk about different ways to assess fit. Item fit is one of the ways where we can assess and determine how well items load onto a particular factor. Now, this is a little bit more subtle and depends on some theoretical constructions and how the instrument's made, etc. There's some different kinds of cutoffs we can have. There's a lot of different information that we can have on this one. And so it's going to be a little bit more difficult than maybe some of the others. All right, well, let's jump right in. So, your textbook and any article that you'll go read online on this topic will show you a bunch of different options. And rather than discussing them all, I'm going to look at three categories that are presented in this classic Hugh and Bentler paper and kind of discuss some options within each relatively briefly. I'll talk about the overall model chi-squared test, talk about some different absolute fit indices, talk about some different incremental fit indices, and then I know I say three categories. This model comparison indices is how I think of this, but isn't actually presented this way in your text or in these classic articles. But for me, again, it's very common to compare different models, and so we'll have a special conversation on what indices are good for comparing models, um, and how we can use those. Again, this discussion is going to be relatively brief and is by no means comprehensive. One of the things that you might see in other more extended discussions is a presentation or even explanation of the equations behind many of the fit indices discussed. And that's just beyond the scope of what we're looking to cover in this class. If you're interested in those, and those discussions are important, even vital in terms of understanding and comparing these and when they're which one is most appropriate, etc. I encourage you to check out your text and the readings assigned for this chapter. And there's again a variety of other readings and even lecture videos if you'd like that go more in depth on the construction of the different fit indices and the relative strengths and weaknesses from a theoretical perspective. All right, so starting out, a model chi-squared test is used to test a variety of different things. We can have them in logistic regression. We can have them all over the place. So this is one type of test that we can do, um, and it is not particular to structural equation modeling or confirmatory factor analysis. This test ultimately compares the fit of our model to a perfect model. We're going to call the perfect model a quote unquote saturated model, but we're going to compare our model to the perfect model. And the null hypothesis is that we're perfect, and we're going to test is there enough evidence to say we're not perfect. So we're going to look to be significantly not perfect. That's not a good thing, but that's what we're going to test. And that brings up the point. Significance is not a good thing. It tells us we're significantly not perfect. So when we do these tests, the evidence of statistical significance, that would be considered bad. How bad? Well, it kind of depends on who you ask. A purist, a classicist would typically say this is bad with a capital B. If your model is not perfect representation of data, get on out of here. It's not even worth it. It's not going to be useful for anything. It doesn't actually reflect the situation because there is a statistically significant difference between your model and reality, between your model and what was observed. And there is some degree of truth in that. There is a difference between your model and what's observed. You are not perfectly capturing reality. So any claims that you make have to come from the perspective of this isn't a perfect representation. On the other hand, more applied researchers kind of say that, we're never going to perfectly capture reality. There's a ton of stuff going on. So as long as I'm really close, I'm not going to worry about it too much. And this is especially true with larger sample sizes. The reason this is true with larger sample sizes is that in larger sample sizes, the tests for chi-squared can get so sensitive to any deviation from the observed variance covariance matrix that it becomes almost impossible to have this p-value be greater than 0.05. That is, we're always going to find a statistically significant difference because any minuscule level of difference is going to be declared statistically significant at large sample sizes. I'll say that on almost every confirmatory factor analysis and structural equation model that I've run in the real world, there has been a statistically significant difference between my model and reality. I'll be quite frank about this. I completely ignored this test. I report it. It's standard to include, but it just is so sensitive with the large sample sizes that typically are required with confirmatory factor analysis and structural equation modeling that the results are just not particularly meaningful or really interpretable. Now, while I say that, one alternative thing that you can calculate based on the same information that's provided, typically we report the chi-squared, we report the degrees of freedom and the p-value for this test, is to look at the chi-squared over the degrees of freedom. This alternative presentation is called the normed chi-squared, and I do glance at this one. I don't report it separately, but I do kind of glance at it. I don't really comment on it. I don't really use it in any diagnostic way, but I kind of glance at it as it just gives me another touch point on how good or bad the model is. The model's fitting. Now, what's the cutoff for good or bad? That also depends on who you ask. 2, 3, 5, 3.841. There's lots of answers here. It's a lot of rules of thumb. It really depends. I kind of like the pseudo theory behind 3.841. It's the chi-squared 95% cutoff with a single degree of freedom. So that kind of makes sense to me, but there's a lot of different presentations on what you're looking for here. I think there's common consensus that you're looking for a number that's not 10. So if you wanted to be relatively liberal with this, you'd probably be looking at below 5. That's probably the most liberal interpretation of this ratio I've seen. But again, I personally don't use this diagnostically, either in the model chi-squared test in terms of the p-value, because it tends to be so overpowered. That is, it's always statistically significant, and because even if the model is slightly different than the data, than reality. And if it's always statistically significant, even if there's a slight difference, that means I just don't trust the test anymore to actually tell me anything useful. In this alternate presentation, it's something I do kind of glance at, but I don't do more than give it a quick glance. I glance at it, say, oh, okay, and then move on to more classic fit statistics. In the line of more classic fit statistics, we have absolute fit indices. So absolute fit indices, according to Hugh and Bittler, and according to their own theory, talk about how well the model connects with the saturated model, that perfect model. So in this way, this is very similar to the model chi-squared. And in fact, many of the absolute fit indices are based upon the model chi-squared. So if you go look at the equations, you'll see them be related to that chi-squared with the saturated model. Thus the name absolute, comparing to this absolute perfection and seeing how well the models align with that. So this is a class of possible indices. There's a lot of things that come into this classification. Some that you'll see that either you'll see in the book or the assigned readings are GFI, SRMR, RMSEA. There's others. I'll just talk about these three. GFI is presented in your book. There's the GFI, the NGFI. There's some spin-offs here. The GFI and the NGFI seem to be not very good performing according to some research. Of course, other research says this is fine, but these are not ones that I tend to use given those results. That said, while I don't use the GFI, I do use SRMR and RMSEA on every report I do. So I report the SRMR, report the RMSEA. RMSEA is typically reported with a 90% confidence interval, looking to see if it's around 0.05 or 0.06 or 0.08, or depending on who writes the cutoff, what the cutoff is. So I do tend to report both of these pretty consistently and religiously. Now, each of these have different cutoffs. I can't say this enough time. These are rules of thumb. These are not absolute hard and fast written in stone rules, but for these rules of thumb, we can go through them. I will say, broadly speaking, there tend to be two directions. We tend to have fit indices that larger is better, and tend to have fit indices where smaller is better. So goodness of fit index is one where the larger values represent better fit. And typically, all of these cutoffs are relatively similar in that adequate fit tends to be around adequate fit tends to be defined as above about a 0.9, and good fit tends to be defined as about above 0.95. So these are kind of typical cutoffs that you'll see rounded to make them kind of align among these things. But for the ones where higher values are better, you're going to be looking at 0.9 as adequate, 0.95 is good for your cutoffs typically. It's what I see used in current research. For the SRMR, standardized root mean squared residual, we have smaller values are better. And so for this, adequate fit below 0.08, that's okay. And then good fit would be below 0.05 when using this number on its own. So again, smaller values are better for SRMR. And actually, same thing for RMSEA, the root mean squared error of approximation. Smaller values are better. And I've kind of made these borders a little bit more fuzzy to align them. That again, adequate fit around below around a 0.08 for RMSEA, and good fit below around a 0.05 for RMSEA typically. All right, so incremental fit indices, and this is just another group. In fact, I think many users don't really care about these definitions. I'll explore in a future slide which ones we care about, which ones we do need to pay more attention to. But incremental fit indices look at proportional movement in relative to a baseline model. So we have our model that we're comparing to some baseline. And sometimes you'll hear this as the independence model or the uncorrelated model. And that's often used as a baseline, but it's not the only baseline that you can use. There's other baselines that can be used. And so we're looking at incremental improvement from that. Within this classification, some you'll see are the NFI, the NNFI, which is called the TLI. That's what I know it as, the Tucker-Lewis Index. The IFI, the RNI, the CFI. So again, there's a bunch in here. These are the ones we'll discuss. NFI seems to be one that we don't typically like to use. On the other hand, the NFI spinoff, the NNFI TLI, is one that is common to use, and I like that one quite a bit. The RNI and CFI are algebraically equivalent in most applications. So which one you pick among these is not particularly important. TFI and IFI, TLI, excuse me, and IFI are not algebraically equivalent, but they perform similarly, and both are typically less affected by sample size. So typically, when I report based on this, I'll have the CFI and the TLI that I'll report. Alternatively, I could report the RNI and the IFI, but for me, no good reason. I just tend to report the CFI and TLI among these. For all these, larger values are better, and these are going to have the same cutoffs that our GFI did in the previous slide. So adequate fit of better than 0.90 and good fit of better than 0.95. So again, larger values are better for all of these that are discussed on this slide, are incremental fit indices. Now, the previous slides kind of talked about relative fit, good fit, generally speaking. So, kind of overall, broad, objective, good fit. But now we're going to talk about indices that compare models to each other. So, model fit relative to other models. First of all, the model comparison indices isn't a formal name, but this is how I tend to think about these. These could be classified as absolute. They're all in their own way spin-offs of this large model level chi-squared. These ultimately allow you to compare the different possible factor structures, so different models to each other. When I say factor structures, what I really mean is just, well, I think all these items load on a single factor. I think all these items load on 2 factors. I think all these items load on 3 factors. Well, I can compare that and see which ones seem to be most appropriate. Typically in CFA, I'm looking to confirm a pre-hypothesized factor structure, but it may be the case that another theory hypothesizes a different factor structure than you do, in which case it might be worth positing 2 factor structures to determine which is the best factor structure, that is, which best aligns with the data. So when we have 2 models where all of one model is part of the other, we call these 2 models nested. Now, I'm not going to go super in-depth on nested models within this video lecture set. I'll just point out that when this is the case, we are able to do a formal statistical significance test comparing the 2 models. This test adds if the more complex model adds anything. So again, if these are nested models, I can kind of illustrate how this model is the same as this other model under this particular circumstance. And so we might have one graphic and then one graphic where we add a line to it, and we might say, okay, that one where you added the line, that is the more complex model because you added a line to it. But it's also nested because all the components in the one without the line are in the one with the line. So I can do a formal chi-square test to test the difference between those 2 models. And again, what this test is testing is if the addition of the line in the more complex model adds anything. If the answer is no, that is, it wasn't worth adding the line, that didn't really add anything to the model fit, we would choose the simpler model without the addition of the line. That is, we would choose to be more quote-unquote parsimonious. Now, if you don't have nested models or you just don't want to think about if the models are nested or not, you can use the AIC or BIC, standing for Akaike Information Criterion or the Bayesian Information Criterion. And I'm sure I messed up the Akaki or Akaike Information Criterion. I never know how to enunciate that, so that's completely my bad, but sorry. Anyway, for both of these, it's important to realize there is no scale. So the only way that you can use these is to compare them to other models. That is, I don't have a rule of thumb. This isn't between 0 and 1. It's not anything like that. All I have is a comparison to other models. So I've got Model 1, Model 2, Model 3, and I compare the AICs among all of them. I prefer AIC to BIC, but I compare the AICs among all of them. And when I make that comparison of the AIC among all of them, I can see that this model is better because it has a better AIC score. And that's it. You don't have any rules of thumb that you can do. This is only for model comparison. This isn't for that overall fit. You can't use AIC or BIC. In general, for these, you're looking for lower scores. Not in general. You are looking for lower scores. Lower AIC, lower BIC indicate a better fitting model. And it might be worth noting here too that for these statistics, these are calculated not just for CFA and structural equation modeling. You can do model difference tests between regression models. You can do between logistic regression. You can do calculate AICs. Happens often sometimes that we'll calculate an AIC or BIC when trying to do model selection in regression. So these are statistics that can be calculated much more broadly than just in confirmatory factor analysis or structural equation modeling, but we can pull those same statistics from more traditional methods into here to assess things like model fit. All right, closing out in model fit indices, why pick? So again, this Hugh and Bentler paper is very well cited. It's the most commonly cited cutoffs paper that I've seen. And the big contribution of their paper that they recommend is don't use one index. Use multiple indices. Amidst their write-up, they discuss how the SRMR is sensitive to misspecification of factor covariance in latent structures. That is, when I have circles, those factors or latent variables, the relationships between them, SRMR is sensitive to whether that's specified correctly, while all of the rest of them are sensitive to misspecified factor loadings within the model. So my recommendation is you pick one of each or multiple of each. So SRMR is going to be one, and then you can pick some of TLI, IFI, RNI, CFI, RMSEA additionally too. From their paper, the combination cutoffs are different when you use two, and that's because when I use two, I have another thing checking on that, so I might have to be more strict in one and less strict in the other, or less strict in both. But in this particular case, the combination of cutoffs yields better results than any single cutoff. And again, that's the contribution of Hugh and Bentler's seminal paper. So all of these are going to involve SRMR, but then we can look at the other statistics. So for TLI, we'd want TLI to be above 0.95 with SRMR below 10. For RNI, CFI, we'd want it to be above 0.96 with SRMR below 0.10. RMSEA, we want it to be below 0.06. SRMR below 0.10. So again, all of these are recommended by Hugh and Bentler as potential cutoffs. Ideally, you'd pick which ones you want to use beforehand. And their goal in this is to combine these results to balance the type 1 and type 2 error. The type 1 error in this case, I guess, would be a false acceptance of the model, and type 2 error would be a false rejection of the model. I guess I'd have to think about that a little more. But in this case, both of the types of errors, what they ended up doing is summing both types of errors, the type 1 and type 2 error in this particular case, and trying to minimize the total error. And that's where these cutoffs came from, is the cutoffs among these statistics, which minimized the total error. For full disclosure, what I tend to use in my paper are these. I tend to report the chi-squared, the degrees of freedom, and the p-value. I tend to report the TLI, the CFI, the RMSEA, and the SRMR. So those tend to be the ones that I report. I might start using the IFI in place of the TLI. They're mostly the same, but IFI might be slightly more robust. But it's important to realize the reason I do these is not necessarily because I've done an in-depth dive as to the theory and think they're better. I have done some work into the theory and do think that these are all potentially valid options, or the ones that I stated are potentially valid options. So I definitely use them for that reason. But one of the reasons I primarily report them is because they are valid options and they're reported by default in the software I use most. So this often comes into play that it's not purely theory that drives the model selection. It is also pragmatism. What is reported in my software? How hard is it to calculate? If it's not in my software, etc. And among the second bullet of options, TLI, IFI, RNI, CFI, RMSEA, all of these I think are things that I would report based on how convenient they are to report, as much as I would report them based on that one is theoretically better than the other. The SRMR, from my perspective, is the exception. And again, that is based purely on Hugh and Bentler's work in terms of their identification of this being particularly sensitive to a different misspecification error than the rest. So I'd recommend the SRMR and then a few others. I have three, again, the TLI, CFI, RMSEA. And then if two of them disagree, I can kind of do a majority vote with the three of them. Referring to the cutoffs, when we have multiple cutoffs, it's important to realize both indices have to pass for the good fit according to Hugh and Bentler's criterion for model fit and good cutoff. All right, so this has been model fit. Now let's move on to item fit. So with item fit in our factor loadings in CFA, again, the factor loadings are, the arrows are drawn in the other direction. So this is kind of the effect of the latent variable on the observed indicator, but is really still analogous in many ways with our factor loadings from exploratory factor analysis. Now, the item loadings can be provided as unstandardized or as standardized, but typically for item loadings, we report them as standardized. And standardized puts that item loading between -1 and +1, and we really interpret that as a correlation or linear relationship. Now, there's, again, not nearly as much consensus on the rules of thumb for these items, and there's a lot of potential reasons. One is we can test for the statistical significance of the relationship. So if I already know that the item is significantly related to the underlying factor, do I need a rule of thumb? What does a rule of thumb really add? The second reason is sometimes, based on theory, we may expect some items to be more or less related. So for instance, sometimes I might be studying a factor where I've included an item to represent a new facet of that factor that really isn't covered in all the rest of the items. So the item loading on that factor might be relatively low, but it might be because that's a new facet that isn't broadly reflected in the other items on that factor. And because of that, it might be really important to keep that item onto that factor, even though it has a relatively lower loading. So in that particular case, again, we might expect some items to be less related to the factor, and that makes it hard to have a cutoff or a rule of thumb when there's so variable of expectations on what that should look like in the first place. Now, of course, everybody wants the rules of thumb, so here's a couple of them. Some say it should be above 0.7, so this would be, you square it. Again, these are kind of correlations, so you can square them to see the percent of variance explained in the indicator. So again, factor is explaining indicator response. So this would say of a cutoff of 0.7 would say we want at least 50% of the variance in the indicator to be related to the underlying factor. So if I respond to a question, I want 50% of the variability in that response or more to be related to this underlying factor coming through my response to that indicator. I don't want it related to other things. Others use the EFA cutoff that we used for loadings of 0.32, which responds or corresponds to a 10% of the underlying response, or 10% of the observed response is due to the underlying factor. Some people say there shouldn't be any cutoffs. Again, it's purely dependent on theory. Anytime you use a rule of thumb, so there's lots of potential perspectives on this. I think it's probably a good practice to try to identify what you think will work best for your study ahead of time, and then to follow that. I think the worst practice is to change your standard because the data aren't showing you what you wanted the data to show you. So if you think that if you're looking through the theory of the items and their loadings before you collect data and say, okay, these ones, they should all be very closely related, so I'm going to set a high standard for them. This one particularly, I think it's still related. It still has to be there. I hired a panel of experts, and all the experts think it still has to be there. I have good reason to think it still has to be there, but I think it's going to be kind of unrelated. So I think that the loading might be lower. If you can pre-hypothesize that and have good reasons for that, that is the best case scenario, because that means that you're approaching this from a theoretical perspective and not really, I guess, p-hacking is one way to say that, but not really changing your model just so that it looks better, even though it's not theoretically supported. So again, you should be able to think through this. You should be able to, after reviewing research, make your own personal decision regarding what your cutoff should be prior to implementing the study. As for me, I think I'd like maybe the factor to be the biggest source of variance in an item. 50% guarantees that there's no other source of variance that's bigger in the item. But I think even if we had like a 33% cutoff, that'd be what, 0.57, something in there. That you know, if 33% of the variance in the item is due to the underlying factor, well, that's a pretty good chunk. And it'd be harder for any other single source of variance to come into play there, especially if the factors have been reviewed by an expert panel and stuff like that, which is how I tend to construct my instruments, or been previously validated. Now, it depends, but again, thinking through my research process and how I approach that, maybe 0.5 to 0.6, somewhere in there might be decent cutoffs. Things that are down to 0.3, low 0.4s, maybe I'm a little more hesitant that those are high loading items on the factor and that those are necessary. But of course, I could run the model with and then take them out and run the model without and see which model fits better. Maybe one closing thing here is it's important to go back to theory, and we'll talk about this here when we talk about you broke it. So amidst the plethora of all of the different statistics, all of the different item loadings, all of the different things you just did, something broke. What can you do? Well, first of all, again, if all of your fit statistics look good except for one, which looks kind of borderline, you're probably okay. That is, and different people disagree on this, but for me, I kind of do majority rules, and I'd like it to be a heavy majority. If it's a bare majority, then maybe I'm a little hesitant about this, but it's a heavy majority and just one of them's a little bit off, I'm not going to worry about it. Similarly, all of these are rules of thumb. So if things are pretty close, then it's probably okay. And I don't mean pretty close as in the cutoff is 0.9 and hey, 0.5 is really close to 0.9. I mean like really close. Like my number is 0.89, the cutoff's 0.9. It's probably going to be fine. But if most of the indices are showing a poor fit, if a lot of the indicators are showing a poor fit, you may need to go back to the drawing board. And it's, I say literally here because remember, we draw out our models. So you may need to go back and start looking at ways that you can add. Now you can edit your confirmatory factor analysis, and we'll discuss a couple of ways that you can look at these edits on the next slide. But sometimes adding one or two paths to your confirmatory factor analysis isn't enough. And so you will need to go all the way back to an exploratory factor analysis. That is a method that lets you, from scratch, come up with how many factors should there be, where should the items load, like just go and let the data drive that, because clearly the pre-hypothesized model just isn't even close. And that's a valid step. If you can't get that CFA to run with a couple of theory-driven edits, then going back and saying, look, we tried, we couldn't get it to run, so we ran an EFA to figure out what the heck was going on, and this is what we found was going on, so maybe this is a new theory going forward. That's an important contribution in its way. Now, it's important to realize, though, once you start editing that model, the whole point of confirmatory factor analysis was analyzing a pre-hypothesized model. Once you start editing, that's no longer your pre-hypothesized model. Now you are changing your model based on trying to get it to fit the data better. But that's not your pre-hypothesized theory. That's just fitting the data better. And there's risks in that. So traditionally what happens is if I start to make edits in my pre-hypothesized model, either through using some tools available from the confirmatory analysis framework, whether going all the way back to CFA and determining the number of factors all over again and which items load on which factors all over again. When you start making edits, you can do that, but your study now becomes exploratory because you are making edits based on your data and you're no longer confirming a pre-hypothesized model with your data. So typically what happens here is that you'll then need another sample to confirm the groupings that you make after you make your edits. So I'm going to make some edits, and now I need another sample to confirm the new model that's based on all these edits that I had from my previous sample. I'll add a bit of a caveat on here. That is, the new sample, while this is a classic view, it's a bit harsh, just a bit, but a bit harsh. If you have an additional path or two, relatively few, that are suggested by theory, these are typically acceptable to add depending on how strong the theory support is and why you didn't add it in the first place. It kind of begs the question, well, if it's based on theory, why didn't you add it in the first place? And that's a good question, and you should plan to have a good answer. For the other things, if you add more paths, if you're just using statistics to tell you which paths to add, if you're going back to the EFA, you should plan on viewing your results modestly. You should plan on them being viewed as exploratory results, making conclusions about them from an exploratory lens. They're no longer confirmatory in nature. And again, you should plan on doing a follow-up study. I will mention your book talks about something I've never seen or heard of before, and it says, make edits and then correlate the factor loadings from before the edits and after the edits. They have a cutoff of 0.9 correlation that seems completely arbitrary, but you know, that's what the textbook says. Again, I've never seen that in practice, and I don't know how. I don't want to think about how many CFA and SEM articles I've read, hundreds. So I've literally never seen that. But that's something that the book talks about. It has a little bit of rationale, but the cutoffs seem completely arbitrary. The practice seems a little bit sketchy. And again, I've never seen it professionally. But if you're in a field where that's common, that I've never heard of before, then that's great. And your book illustrates how to do that and what to do. All right, so how can I improve the model? What are the three methods? Well, the first one, and really the only one, is theory. This is far and away the best method. And what it is it says, go look at the factors, go look at the items, and figure out, theoretically, which items should be loaded onto which factors. And that's what you're supposed to do before you come in the first place to run a CFA. But if it doesn't fit, then maybe you missed something. So you go back and say, what did I miss? Maybe two items have a special relationship because they're talking about some particular aspect of something that you need to say, okay, I'm going to let these two items have a special relationship. Maybe you initially believed your factors were completely unrelated, but maybe they should be correlated. So ultimately, you're looking for the theoretical explanation and relationships as to why you should make changes to your model. Now, I'm about to present a couple of statistical methods, but theory is the only reason typically that you're going to be allowed to change your model within the same data set without saying this is completely exploratory. And you can say it's completely exploratory too, but even in complete exploratory, you should have a theoretical reason. Remember, in exploratory factor analysis, that was the most exploratory you can get. Even in exploratory factor analysis, we looked at the high factor loadings and said, okay, what does this mean? What's the theory that connects these? So all of it comes back to a theoretical interpretation. A very, very, very common statistical method is to use the Lagrange multiplier, or what some programs call modification indices. These are not always identical to one another. I prefer the term modification indices. I think it's more broad. But ultimately, this determines how much help adding a particular path would be to the model chi-squared. So how much improvement would that bring? So again, these are often presented as improvements on the chi-squared. It's really important that you make these one at a time. So here's the process I would do with the modification indices. I would look at the top 5 biggest modification indices. These are the ones that are going to help the model the most. So I'd find my modification indices, find the biggest 5 or 10 or biggest number of a few, and figure out among those which ones are theory supported. And so I'm going to implement the highest theory supported model edit that I can following this modification indices method. I'm going to implement that, but I'm only going to do one at a time. So how it works is I would find that theory supported thing. It's a very high modification index, maybe the top one or the second to top one. Okay, that one's theory supported. I get the theory. I completely see where I went wrong. I can't believe I missed that. And so I put that in. I run that in my model, and then I recalculate modification indices. So I don't put in the top 10, even if they're all theoretically supported. What I do is I look at the top one that has strong theory support, and then I put that one in my model and I rerun, and I see how much did that change. Because what can happen sometimes is after accounting for one of these, all the rest of them are taken care of. So I just do one at a time here when I'm doing modification indices, but it's really important. I don't just drop in the top 10 edits into my model. What I do is I look at these. These are potential suggestions that the program is making, saying, hey, why don't you check these out? Maybe these could be good. And you, as the researcher, have to determine, is there theory support for that change? Kind of in the opposite direction, we have a walled test, which really looks at what paths are currently in the model that could maybe be removed. Again, we can look at this for all of the paths that are in the model, but even if a path is very statistically insignificant and can absolutely be taken out statistically, etc., we have to determine if theoretically that removal makes sense. If theoretically that removal doesn't make sense, you leave it in the model, even if it would improve the model to take it out. If theoretically that does make sense, you look at this and you say, oh my God, I can't believe I put that in there, then you can take that out and feel justified in doing that. But again, it goes back to theory. But the modification indices and the walled test are kind of statistical suggestions. They're a list of things that the program gives you. It's like an assistant saying, hey, what do you want to do? And you have to look through them and say, yes, this one makes sense to do, or no, this one doesn't make sense to do. And based on that, you can edit your model and hopefully improve it. That's the goal anyway. And again, if you can't, that's okay. Just go back another step. Go back to exploratory factor analysis and see, okay, well, I can't figure out how these things go together. The theory doesn't seem to support it. What does EFA say? Maybe I have the wrong number of factors. Maybe EFA can tell me a new number of factors. Maybe I have items completely on the wrong factors. Maybe EFA can tell me that. So even if you're not finding good modification indices, you're not finding good wall tests, or you find strong modification indices, but you can't think of a theory that supports that, you still have steps that you can do that are going to add to your understanding of the data you have. So don't feel like you have to force anything. You certainly don't have to force something through. It's all about using your data to come to a better understanding, either confirming your hypotheses, or if it's not confirming your hypotheses, informing you of what the relationships in the data are so that you can potentially come up with some new hypotheses or new theoretical explanations among these variables. All right, well, this has been a discussion of model fit and item fit and some methods that we can go about improving models. In the next video in this lecture set, we will go into a quick example demonstrating how we can utilize the stuff that we've been talking about.